Constants are symmetric. Okay, instead of one oscillator, we've got two now. And for the time being, we're going to leave out the friction. And in fact, we probably will not discuss that in this course, but there's a whole section of that in Unit 4 where we work out the Green's function for, well, an arbitrary bunch of oscillators. And you can take a look at that on your own time. The thing about solving it this particular way, we're going to attack it the most common piece of mathematics that all of us use for both classical and quantum mechanics of vibration and motion. And what I'd like to do is show you some shortcuts, and also there are more than shortcuts. There are things that make sense out of the whole calculation of eigen solutions, that is, eigenvalues and eigenvectors, and a way to make projection operators, item projection operators in particular, powerful for all kinds of things. So this portion of our lecture will deal with the mathematics, and I'll apply it to a matrix. Is very seldom seen, if ever, in a quantum mechanical situation, because it's not symmetric, it's not Hermitian. But this particular way of attacking eigen solutions has no problem with that, and it could be complex as well. I've left that out for this particular example. So the old 1, 2, 3, 4 matrix is what we'll work with in this section as we discuss the theory for diagonalization, which we need in order to obtain the solutions to coupled oscillators, starting with 2. And then what I'd like to do is go ahead and show some animations of the thing and discuss some of the numerical things that happen with that. On the way there, we'll mention diagonalizing transformations, which is important and part of any calculation probably that you would do with this. And the examples that we'll show are the ones that I pick up, and I have names for them: bilaterally symmetric, asymmetric, diagonal. That sort of notation will come in the next lecture, where we'll go at this thing from an entirely different point of view and use spinners and get familiar with that quantum mechanical technique. But it really came long before quantum mechanics was invented, as I've already said. Hamilton's quaternions are the algebra, and they're really powerful for different reasons than this particular thing that I'm showing today. So anyway, let's go ahead and this is the machinery that we're talking about that will be simulated here, and there it sits. Got a spring connecting two pendulums. So this is a sketch of that. Now, these particular pendulums have mass that's the same for both, but by simply changing their location, this is a big thread here that you change to break the symmetry, we'll start off with a case of symmetry, that is, with these two masses equal, the two lengths equal, and then this one coupling between them. This is analogous to just two masses sitting on an air track or something as frictionless as possible, and connected by possibly three different springs, and possibly being different masses. So its general problem is right there. This is a prettier picture of that problem, in which we indicate the coordinates as distances from where this thing wants to sit if it's left alone, its equilibrium position. Now, this last one here makes a point which I think is important to think of both mathematically and physically, and that is a single mass with two dimensions at its disposal. That is a two-degree of freedom thing where you have x and y, or x1 and x2 as the coordinate dimensions, and the springs are whatever angles you want to put them. That is quite the same mathematics as this one, where you have two one-dimensional moving masses. So keep that in mind for things that come up later. Now, when I want to make a Lagrangian potential and everything that goes with that, the kinetic and the potential energy, for discussing this system, the basic idea here will be that we turn this into a matrix equation, the actual equation of motion, which is written down in the lower portion of both of these slides. There's Lagrange's equations that we're seeking to obtain inside of the motion, but first of all, just solve these couple differential equations. So we've got the force given by minus the gradient. Gradient has two dimensions. Whether you're talking about two masses or one mass like that, the idea of all of this, in this particular lecture, we would tackle this thing by matrix methods, is basically boils down to finding the Eigen solutions of a matrix. Well, two matrices at first, one involving the masses, but I'm going to fold that one into that thing by taking the inverse of this, multiplying it by that. That gives you one matrix, an acceleration matrix. This is two accelerations here, governed by whatever the coordinates are at a given moment and the couplings between these. Now, go back to here. The simplest way to write the potential is to simply put the difference, and this is the coupling spring right here, the difference of the coordinates from their equilibrium position, which is shown by the little shady ball there. That is the distance off of the equilibrium for this one. This is the distance off of that one. And the potential energy will be the square of the difference of these two coordinates. So that's the coupling term right there. The rest of it is just two harmonic oscillators using the Hooke's law for their springs, K2 for this one, K1 for this one. So make sure that everyone is clear in what this is giving us, what this equation is that we are seeking to solve here. So there's the clever way to write that equation, and we'll be using fat letters to indicate both operators, in this case the mass operator and the ket vector. We're going to use the notation that was intended for quantum mechanics for this classical problem. And that is worth doing right now, but in the next lecture we're going to make sure that you see that the two-level quantum system is a Hamiltonian system. That is, classical mechanics and quantum mechanics using the same mathematics if you play your cards right. Okay, so the K that we're talking about here is this thing right here. And generally, especially if the masses are different, this would not be a Hermitian matrix. That's why we're using techniques that can solve matrix 1, 2, 3, 4. And this is a discussion of what you could do. This is something you could do if you wanted to deal with something that had different masses, and if you rescale each of these x1 and x2 to some queer coordinates, q's 1 and 2 with a scale factor, it's possible to make an equation where these two coefficients are then equal, even if the masses are different. Now, I'm not going to make a big fuss about this thing, but it is based on an important relationship we call the reciprocity relation. If you're just dealing with something that's described by the potential and it's a function of these two coordinates, x1 and x2, then the fact that you can flip the partial derivatives, that symmetry, lets the change of f1 due to moving x2 be equal to the change of f2 by moving x1. And you see these reciprocity conditions in other situations. If you've been studying electrostatics, you have some masses sitting, or I mean some metal spheres, say, with different charges that have been put on each of them. Then you can say the potential change due in putting such and such a charge on this one is the same as, if I take that charge and put it on this one, they'll be changing the potential by the same amount. With similar symmetry. So that makes us always be dealing with, if you play this game, with symmetric matrix. But I warn you, this particular way of doing things, this forced symmetry, you might say, can give you situations where you get complex numbers for frequencies. All right, so what we're going to deal with is just this guy right here. And the idea is that eigenvectors exist for this thing. And it certainly makes it a lot easier to solve the problem if M1 and M2 are equal. But whatever that situation is the case, they are going to be equal for any system using a spring. So let's get this thing up to speed here. This is what we're really dealing with here. So we're going to take, just for the simple physics that we'll do here today, a case where the masses are equal. So we're going to take a symmetric situation, but not really use the symmetry very much. We're going at it using the same techniques we'd use if it was a completely crazy thing like that. Okay, let's see if there's anything else I need to say about that. I think not. Anyway, there's a graphical way to see what's going on here, and that is, particularly if we can ignore the situation of non-symmetry by making the masses equal, then I can have a nice plot of the potential energy as a function of x1 and x2, and this is what it comes out to be. We now have an off-diagonal component in our little K matrix here. And as a result, the ellipses that we worked with when we talked about quadratic forms before, now the ellipse is slanted. In fact, it's, if these are equal here, then it is slanted 45 degrees. But whatever that angle comes out to be, whatever the plot comes out to be, if we can describe all of our potentials just with that quadratic form there. This is a quadratic form now that's just based on coordinates, not velocity or momentum that we started this course with. This is where you see the most common use for quadratic forms in terms of dynamics of the classical oscillator connections. And the idea of a gradient at each point is now kind of obvious. It was a little bit abstract when we talked about it before. But here, it's pretty obvious what it is. Basically, you're asking, our equation of motion is mass times acceleration equal minus a mass, a spring hook law matrix times x, but this hook law matrix has got off-diagonal components. And the idea is to see what would happen if I apply K matrix to a vector x. Well, remember how we worked that out when we were talking about a Hamiltonian or a Lagrangian operator. We would simply look at the tangent line to that, and the vector would be perpendicular. That's the gradient that's occurring at this point. I just slide it down here so the back end of the vector goes through origin. So there's a geometrical thing describing what sort of force you get. Well, it's pretty obvious. If you're sitting here and you're not moving, the first thing that's going to happen to you is you're going to go down the fall line. The fall line is going to be in that direction right there, in the direction of the gradient, but toward this way. Then you take off and do all sorts of crazy motion here, which we're going to discuss. But that's the sort of geometrical picture of what we're dealing with here in coupled oscillations. I call it Bear Valley, after a ski resort that doesn't exist, but there is something like that in California. It's just not as simple as this one. The basic idea is that you've got two kinds of ski runs to pick from that are extremes. One's extreme in easy skiing, and the other one is the extreme in professional, difficult, dangerous skiing. In this case, this is the gentlest slope right there, the one that's going, say, in the northeast direction, the northwest to southeast line, however, this one right here, this blue line right here, that's the advanced slope. The topography lines are much closer together, meaning bigger gradient, than they are on the beginner slope. And then it's something between those two in between. So that's one way to just sort of see what's going to happen with this system. And one of the things that you realize is that if I get on one of these lines where the force is always, the fall line is always along the track I'm going, I will stay on that track, and that will correspond to an Eigen mode of this system, the one with the low frequency, the slow axis. Okay, and then perpendicular to that, normal to that, is the fast axis. Again, gradient always along the direction that you're moving, so you stay on that line. So one of these modes is a slow swing back and forth, and the other one is a fast motion back and forth. Slow mode, fast mode. So that's the end of the discussion of this thing qualitatively, but it's worth having that before you do the calculation, and you want the calculation to give that result. Okay? So, the beating and all that, you could check that right here by doing this, but I'm going to go ahead because I want to get through this mathematics before we do much with the physics. So the solving for this matrix 1, 2, 3, 4 begins now, and the discussion of it is important for practically anything you do in physics or mathematics. You're always worrying about eigensolutions of something. How do you worry about them? So we're going to consider a case where we had maybe a 3 by 3 matrix or whatever, 10 by 10. As you go up in dimension, the calculations that we're going to describe here really don't change, except that they get more difficult, to get more lengthy. You've got more algebra. And it's going up roughly cubic with the dimension. Okay, so you have to take that into account. Anyway, with 2 by 2, it's pretty easy to describe everything we're doing. So on this side of the screen, we'll work out the 1, 2, 3, 4 matrix, and on this side, we'll use black letters to indicate a general case in the algebra for each step in this will occur there. So the first thing is we give it a try, a blind try to solve this eigenvalue equation. And the first thing that you might think to do is just subtract this vector from this combination here. And that just means you get 4 minus epsilon and 2 minus epsilon times xy is going to equal 0 vector. All right? And then maybe you're not thinking too clearly, so you go ahead and you get out Kramer's inversion. You remember how that works. If I had an A and a B there, I would stick A and B right there in the determinant to get the x solution, and then I divide by the determinant of the matrix. And same determinant right here, except now I'd move the A and the B over here. And that would give me the x and y solution to a linear equation. Or when it might not. In this situation, we got a problem because this is 0, so is that. And yeah, x and y equals 0 is an eigensolution that nobody's going to pay you for. In fact, if you present it, they will fire you. Okay. So this isn't going to work, right? You're in trouble. Okay, so the question is there a situation where that would not be an impediment, that this could work for us, okay? And the possibility of getting non-zero results occurs if, and only if, the determinant of this matrix is 0. So you have 0 over 0 in determinant form, okay? Then you at least have a possibility of getting a non-zero result for both of these. Well, the equation that demands that is called the secular equation. Where did that name come from, right? This is what you're talking about back when science was just getting started. The church controlled everything, and they were not particularly happy about science. But when you started to do things, they started calling the names of things that really worked well, the secular something. Okay, and this is no exception. So we use this to this day. We call the equation determinant of the matrix minus the unknown epsilon, usually used to describe eigenvalue, lambda, more common possibly. But in any case, I go ahead and I work out this determinant, set it equal to 0. And it's really easy with a 2 by 2 matrix to work out that determinant. Here I just was working it out. This times this minus this times this. Okay, so that works out to a quadratic thing, and then that extra minus 1 times 3. And I've got an extra 8 here, so 8 minus 3 is 5, and epsilon squared minus 6. Okay, well, I could have just written this thing down, and this is what I point out. Secular equations are really easy for a 2 by 2, because I only have to have the determinant. That's the determinant of the matrix 1, 2, 3, 4. And then this one, I've got a very special case of the sum of diagonal minors of the matrix. That's what I'm going to be needing. And it will be the k by k. We've got a 2 by 2 diagonal minor, which is the matrix itself. And then you've got just the sum of the diagonal elements, which are numbers. So this really gets easy for a 2 by 2. I just work out the trace. That's the sum of the diagonal. 4 plus 2 is 6. So 6 goes right there with a minus sign, and that you have to be careful about. And the minus, this is the formula for the general case, but this is what we've got right here. So epsilon squared minus 6 epsilon plus 5 is our equation that gives us the eigenvalues. Okay, so we've got the eigenvalues. We've got something that's going to turn into a frequency value for a spring system that had this, if you in fact had such a system. So the idea, of course, is that this is an algebraic equation. The fundamental theorem of algebra says this is always factorable if you get to use complex numbers. Here we get it with real numbers. So we're off to the races, so to speak, here. But then something comes up, because any physics problem that uses diagonalization and eigenvalue solutions has got a information storage contrast with respect to how much information is contained in the eigenvalues. If you're just taking spectra, well, that's all you need. But if you're actually trying to figure out what's making that spectra, there's n of these, but there's n squared components of the eigenvectors. So most of this is about getting the eigenvectors. Okay? And this is a really important mathematical idea, theorem, beautiful step that if I replace the secular equation epsilon by the matrix itself, that is, if I take this secular equation right here and stick a matrix in for each of the epsilons, this thing right here, this epsilon squared minus 6 times the matrix squared first, and then minus 6 times the matrix plus 5 times, and you replace that by unit. That is, you replace every one of these numbers here by a number times the unit operator. So given that you factored this thing, you just write that down. That's what we're going to work with. This is the thing you need to understand. And the idea of that, this gives us a zero matrix. That is, if you work this clumsy thing out here, unless you make an arithmetic mistake, that's what you're going to get. That's the Hamilton-Cayley theorem. And it's true for all matrices, whether they're diagonalizable or not. And it's really kind of hard to prove that. That is a fairly difficult thing, which I've, in all my years of working with, have not yet discovered a way to just see that. Except if it's a matrix that like we work with in quantum mechanics, where I know I can diagonalize it. If I know I can diagonalize it, then it's obvious that I'm going to get a zero matrix. Because each of these guys it's going to contribute to a factor that will make things 0. So this is a big point in the mathematics of descent, which we're not completely doing here, but we're dealing with matrices that we claim we have diagonal thin. Obviously, when I write it out with a matrix like this, each one of them solves an eigenvalue equation that gives 0. So you get 0, 0, 0, no problem. Okay, but using this result, that's the thing that is really cool about that. And that is writing out the factored form for the this, and then taking it apart. Here's the factored form right here. I first look at that factor, then I look at this factor. I use that to get my eigenvectors. That's what these, and these make projection operators, this thing right here, this thing of replacing the factor j, say the second one, by a unit operator. Okay? In other words, just multiplying what's left together to make something called P2. Then if there's a third dimension, well, that'll be called P3 or Pn, nth dimension, and I put a 1 at the very end of this row of factors. Here we only have 2 to do. So here with P1, I eliminate the factor that had the eigenvalue number 1 and leave the eigenvalue number 2, which is 5 here. And I do the same thing for the second one. I put the one that was 5 here, just equal to 1, and I take the matrix minus the first eigenvalue, which is 1, the way we've set it up here. First eigenvalue, 1. Second eigenvalue, 5. Okay. If I do that, presto changeo, I get a matrix that has the actual eigenvectors sitting in the columns, multiplied by a number, which we're going to quibble about in just a minute here. But these two vectors are the eigenvectors, up to a factor, and it doesn't matter what factor you put on an eigenvector, it's still an eigenvector. Okay? So that's the main trick. That's the trick that's making all of the powerful stuff that's going to be happening here. And I'm showing it in all of its glory right there. This is what we're going to work with. The idea that by doing that, the matrix times this projector, and this projector, you see, has that one factor missing. So when I multiply the matrix by this projector, I just get the projector back again with the eigenvalue that I threw out. That guy right there, or this guy right here, each one of those, this is the second case, I have here an eigen operator. This thing right here times the matrix gives the eigenvalue times that projector, and so forth. So right now, if you don't care about normalization, all that kind of stuff, you're done. You've got a set of eigenvectors. Now, the question is, which column do I want to pick? They're both the same. One's always a factor times the other in this situation where we only have distinct eigenvalues. Now, that's a catcher. That's a catcher right here, okay? For what we're going to do at first, I need the eigenvalues to be distinct. No degeneracy. Degeneracy bad, okay? Actually, degeneracy is really good. When you get degeneracy, the whole problem becomes easier. We'll see that later on. Today, we're distinct eigenvalues. Okay, let's see if there's anything else that I need to make at this point. Because basically what we now have to do is find out what factor should really go with each of these projectors to make this powerful. To make this so that you can do other things than just write down the eigenvectors up to a factor. So that's coming now. Now, I did fail to mention one thing that we should keep in mind as we're playing with these algebraic quantities. And that is that all of these things are made out of powers of m. Now, m commutes with itself, right? This times this is equal to that times that. But m squared times m is also equal to m times m squared, and so forth. So any power commutes with any other power. And therefore, these projectors, each of them being linear combinations of these powers, will commute with the matrix that makes those powers. Okay, so that's going to allow us to do both the bras and the ket vectors. We can get bra vectors out of the rows of these projectors, while we're getting the kets out of the columns of these projectors. That begins to get powerful there. And if it's complex, they're going to be conjugates of each other. That'll be quantum mechanics, right? But for a typical matrix that isn't symmetric, we can handle that. And we, in fact, see a very beautiful thing. We see the dual space that goes with the solutions very nicely here. So, this is what we're after. And there's a formula written out in the way it very often is when you see this. This is actually called Sylvester's theorem. And I keep it up on the wall over there because it's really important, along with all the things that it engenders. So, let's go here and look at our example matrix. This is what we have with the first factor of the Cayley equation, Hamilton-Cayley equation missing. This was the one where the second factor is missing. The first eigenvalue is sitting there, second eigenvalue is sitting there. Okay. Now, one of the things you'll notice right away is that if I put these two factors together, I get the Hamilton-Cayley equation plus some extra factors. Hamilton-Cayley equation is 0. So that makes these two operators orthonormal or orthogonal. That is, the product of those two has to be 0. Because it's just reconstructing a Hamilton-Cayley equation, which we've claimed is always 0, totally 0 matrix. Okay, so we're going to make use of that. But as I just pointed out, we can come from either side with the matrix, even if the matrix is a lopsided one like this one. Now, the multiplicative properties right here immediately feed in if I'm going to figure out what's the product of two of these projectors. These little, I call them proto-projectors because they're not quite normalized the way I want them yet. That's going to come down here, and it'll be the uppercase letter that I use when I describe it. And they kind of look the same. This is what we're going to be turning into an uppercase P in just a minute here. But the idea is that, okay, I take Pj times, now what this is going to be is a product of m minus all of the eigenvalues except the one we're interested in for pk. So all m except k is in this product. Well, for us that's only one thing, the other factor, just there. No product sign needed. But as soon as you go to 3, you're going to have two things, a product over two things that haven't been left out. And the P is going to come through and it's going to see the M, and it's going to give just exactly this right here, an eigenvalue that goes with Pj, namely epsilon j. And then we have the epsilon M sitting there. So this becomes a product over differences of the eigenvalues. All of the m's not equal to the k that was the eigenvalue associated with that projector, that p sub k. Okay. Now, if j and k aren't equal, well, this product kills it. But if they are, if j is equal to k, then pk here, and it's looking at all of the m's except k, so you don't get a 0 from this thing. Basically what you get is whatever this number is times pk. And that's the number you want to divide by. That's the thing that's going to determine a kind of normalization for these things. That's happening right here. Okay, got the results shown on the other screens here. Okay. So, the actual, and this is a really funny name, idempotent. It's not to be confused with impotent. In fact, it's anything but impotent. It's the powerful operator. Okay. Uppercase pk is the lowercase p divided by that thing. That's the product over all of the m's except k. M not equal to k, if you can't read the fine print here, that's what it says. Avoid getting a 0 in the denominator. If you have no degeneracy, you're never going to get a 0 in this formula. Okay? Now, idempotent is kind of weird. It's an operator which, when squared, gives itself back again. Or when raised to any power, gives itself back each time. Okay? Kind of a weird operator. Kind of a lonely one, right? Now, our little situation with a 2 by 2 is we've got to divide by 1 minus 5. Well, that's a minus, which turns these, turn off diagonals into a minus to get a plus number, 1/4. And this one, same thing. Now I don't have to change the sign. Those two operators right there are idempotent. I multiply this by itself, 0. I get itself. This one, itself. This times this, just like that, 0. Adding factors didn't affect that. Orthogonality sort of thing. Okay, so this is the deal, sort of summed up here. We've got these projectors that obey Eigen operations. Scaling them doesn't affect it. And we've got the idea that they kill each other. Okay, if J's not equal to K, you're out of here. But if it is, welcome home. Okay? All right. Let's get all of this and the next stuff on this screen here. Because this is where we get to actually see the vectors that come from doing all of this. And I'll show them here first. But before doing that, there's a funny thing that we can do, and this is I call gauge scaling. I've never seen anybody, but you know, the gauge, the scale of each of your vectors. You want to change that? Because we are going to plot these things. So I might want to put a K1 that makes this particular vector here bigger than it. But basically what I'm doing here is I'm taking the square root of everything. I've got a 1/4 here, so I put a 1/2. Okay, and then that specifies a 3/2. So I've made it an outer product of a ket with a bra, and if I scale this one up, I got to scale this one down. Whatever it is, those have got to cancel each other, so that when I do a 1/2 times a 1/2, I get 1/4, which is here. And the minus a 1/2 times a 1/2, I get a minus 1/4 here. Okay, and then when I multiply this thing by that thing, that's this number right here. And if I multiply this by that thing, well, that makes a plus number right here, but it's going to be 3/4, you see. So I basically just took a square root. Now, if these numbers are minus numbers that you're taking square root, you can put an I in there if you want to. This can be complex. It's not going to hurt to have these things. And then this can be a different number than that one, although I don't recommend that. We'll see why when we look at the pictures of these things. So that is the picture right there in the middle screen. I'll put it in this screen too, and then I'll talk about it right here. What you get when you do this is you're pulling from this product here the ket that goes with 2, the ket that goes with 1, those are indicated in blue here. Here's the ket that goes with 1. Okay, it's 1 minus 3 times a 1/2. I'm not changing K1 to any, I'm just letting K1 be 1 and K2 be 1 here. But if you didn't like this thing being so long, you could put K1 to something that would shorten it up. It's better to just kind of leave them the way they are and see what happens here. This is the ket set right here, the blue things. These are the two kets. Notice that they are not orthogonal. And that's because this is not a Hermitian matrix. But this formalism takes care of it very nicely. Now you have the contras, I should say these are the covariants, and these are the contras. This is the dual space that goes with this operator, 1, 2, 3, 4. Okay? So there, those two, and these two guys right here are not orthogonal. They've got a very small angle between them. Okay? But this one is orthogonal to this one, nice big square right there, and this one is orthogonal to that one. That's because of this. So we've got a dual space that's mutually orthonormal. Presto, right? I mean, that's the magic of this dealing skillfully with the projectors, which I rewrite the actual product that makes the matrix, and that's what's really powerful, is the fact that these matrices are a sum of the large P, uppercase P, projectors, and mutually orthonormal. Okay, I'll put that thing. The operator orthonormality is really very much a powerful thing for this whole formalism based on Hamilton-Cayley theorem. Okay, but here's the one that is really quite amazing. This sort of comes out of the blue, and we're going to have a little bit of time. I have a good proof of this one. It's weird, but it's good. First of all, the sum of these two projectors that we've just produced here, and let's just go back and look at the ones that came from the simple formula. I sum these guys up, and the off-diagonals cancel completely, and the diagonals come out to be 1. 3/4 plus 1/4. But here 1/4 cancels minus 1/4. So the sums of these two projectors, and now I'm going to use some Dirac notation for real. This was just kind of faking it right here, but that's, I don't think Dirac had anything in his book that shows the power that's behind what we're doing here, but he wrote an entire physics book during World War II in which he called Ketz alphas and Bras betas. And you can imagine what a mess that was. The whole book that way. And then, but towards somewhere in the middle of that book, he says, "This is crap. I got to keep going, but I've got to have a different notation." That's when the Dirac notation. And then he wrote a book right away where he put the Dirac-Bra-Ket notation in place.
Fixed himself.
You get a lot of money if you can grab one of those first books. They're very valuable. They never got published. Okay, so that is, I know this because of a fellow named Jan Smit, who was kind of my mentor after Left Feynman, is a Dutchman. And if a Dutchman tells you something, it's probably right. They are amazing. Okay. Anyway, he told me a story. He read that book because he was in the middle of the war, and Leiden University was one of the places where the Nazis didn't go. So he could be safe there, and he wouldn't be picked up and put on the front.
Jeez.
So he sat there and he copied Dirac's book with the alphas and betas. Okay, interesting history. All right, let's see something here that I think is a punchline for all of this, and something that we can use for other things than just doing our calculations of eigenvectors and eigenvalues. This is going to give that to us, but here's something I think that's really neat. And if these projectors all add up to 1, that's called the completeness relation. What's complete about how can you justify that name? And furthermore, if I multiply this thing, the 1, this unit operator, by 1, each time the m hits a projector, it just gives the eigenvalue times the projector. So you can write this matrix. This is, I call, the spectral decomposition of the matrix M, the operator M, abstract operator M, if you will. So each one of these things just gives you the eigenvalue times P1, eigenvalue times P2, eigenvalue number n times Pn. And that's really quite nice, okay? But there's more to it, because this is very powerful, you see. If I want to take a function of a matrix, and boy, there are cases where we would like to do that, and do it easily. This is the ticket. This is really cool. just to check that our 1, 2, 3, 4 is adding up with eigenvalue 1 and eigenvalue 5, okay, to the original matrix. You see that here. Okay, that is the spectral decomposition of the matrix itself. But what if you would like to take the square root of this matrix, or raise it to the 500th power, or 50th power? I'll do the 50th power first here, okay? So let's suppose you want to do the 50th power of this matrix. It has to multiply by itself 50 times. That's kind of laborious. Instead, you take the eigenvalue and put it to the 50th power, and I was going to write that rather than, that's just 1. And then 5 to the 50th, well, that's a big number. I'm not going to write that out. But anyway, I just add these two matrices up. There's closed form right there. Okay? Suppose you want to take square root. No problem. Square root of 1, square root of 5. And it's plus or minus, so I've got actually 4 solutions to this. There are 2 square roots, but for a matrix 2 by 2, there's 4, and for 3, so the number goes up each time by the n squared. So I have here 1, and I have here the square root of 5. I put that together and check it out. Sure enough, you square it and you get back the original matrix. That's kind of powerful right there. Now, how does that work? What's going on here that I can get away with that? You have to think about what would happen each time I multiplied this whole expression by itself, say. If I just wanted to get the square of the matrix by doing that, well, all the cross terms are 0. And all the diagonal terms are just squares of an idempotent, which is the idempotent itself, right? Times whatever that is, and it'd be the square of epsilon 1, and this would be the square of epsilon 2, and so forth. Easy way to square a matrix as well, right? Once you've got the projectors. So anything you want to do with a matrix, get it spectrally decomposed, then you're just taking the eigenvalues through whatever function it might behoove you to do it at a moment. And later on the next lecture, we're going to be doing a lot of exponentials of matrices. That's a really quick way to get it if you're coming in without the technology that we're going to be developing then, which doesn't use this. So that's what I would like to leave you as far as the mathematics that we've developed today here. That is something to put in your logbook. This is a tool that I recommend highly. Okay, now we go on here just to look a little bit more. I want to make sure that you see that orthonormality and completeness are kind of duals of each other as well. And I also want to
Professor Harter,
try to prove the completeness relationship. Yes?
before you leave this slide, could you discuss a little bit about if you do vary the case of 1 and the case of 2? Doesn't that change the relative lengths here in your graph?
At any time, you can take this guy right here and this guy and change them. That is, K1 can get bigger. Okay, and if you do that, the blue guys are going to get longer, and the dual, the reciprocal space is another way to say it, is going to get shorter. I think that's an important idea, right? In other words, there are different units. There are different parts of things. Very often you're going to have something that's in per space time, like a wave vector, times the actual position in space, which is x itself. The other one is inverse x, inverse distance, okay, or inverse space time. So mainly it's just a graphical change that would occur. Absolutely no change in your computation by doing that. Okay. Orthonormality is operator. Looks very different from the equation. This is almost magical. We haven't proved that completely in a way other than to just write it out and see that it works. Where did it come from? I've got to still do that. But if we take this thing into Dirac notation, then the orthonormality just comes from taking this ket bra and putting it with another ket bra, so the two bras just give you a number. In this case, it's a delta, Ij, 1 or 0. Okay, so there's your orthonormality using Dirac notation. Okay, and that's important to be able to go back and forth between this fat vector formalism and the stuff that you get in modern quantum mechanics books. And then the sum of them is this. Okay, still, this looks very different from this. But when you represent them carefully, they kind of start looking the same. So if I'm actually looking at something that involves, say, position x and y, and then an eigenvector epsilon and epsilon 1 and 2, okay, I could say, oh, I'd like to look at this particular quadratic form with x and y, and then I rewrite it by summing over the projection operators, right? This is the chainsaw sum rule for scalar products, okay? I just stuff in that 1 equals ket bra, ket bra, ket bra, okay? And I get a sum over this ket bras inside x and y. And that's not too different looking from when I do the same thing just to check out the scalar product of the two eigenvectors as opposed to the two position vectors. Then when I get a thing like this, well, it's just a sum over, now it's ket bras involving those position vectors. Same notation in each case. It's epsilon, epsilon, and this is xx. Okay? So now there's the completeness and orthonormality. Well, which one's orthonormality and which one's completeness? They look the same in Dirac notation, except for changing symbols inside the kets, right? And it gets even more squirrely when you start talking about wave functions that are of a continuous sphere. Now you're walking into what's called out of Hilbert space into something called Banach space. Space with these continuous variables and the calculus that goes with a summing using an integral. Okay, that gets weird, and you use as a very weird delta function, the one that Dirac invented in order to get the Banach spaces working. So here they kind of start to look different again, because this one's going to involve an integral. Well, this one right here kind of does too. But still, now we're really seeing, if you're talking about wave functions, and these are all very important for quantum mechanics, but also for our classical, because we're going to be doing the two sort of on top of each other. Okay, so that's thing. Now, where did this crazy thing come from? This thing. I scratched my head for a long time. I just said, well, go work it out. And you start working out for 3x3 matrices. It covers a page, and you say, oh yeah, it works, and so forth. How is it that I can put this in some sort of framework where I can prove it? I can prove that the sum of all the projected operators just gives me one unit operator. Well, there is a thing called Lagrange interpolation. It looks like this. Here it is. This is how you approximate, this is how you rewrite a function that has been given to you by some data randomly distributed over the independent variable, where you know where its value at x1, you know its value at x2, and so forth for n points. You can make a polynomial that goes through all of those points by following Lagrange's prescription here. That is, whatever you are given for the value at xk, you then multiply it by a pk that looks just like our projection operator, except it's no operators, it's just algebraic numbers sitting there. Okay, the idea is that this thing has the properties that make it do what Lagrange wanted to do. It's an interpolation formula. That's the name that's given to this crazy thing. So each polynomial has zeros at each point x equal whatever data point you happen to use, except where x is some other thing, and then, well, at that particular value, you get a 1, just the number 1. These things cancel each other. Okay? Pretty clever. Pretty clever. Okay? And you might think that this would be really useful for interpolating functions. Okay? You get some data, you get Lagrange's guy out, and it draws, wouldn't it be nice if it drew the curve that you really wanted between all those points? The problem with this is it's much worse than the spline interpolation, which kind of does that. This one, very often you'll have it hit here and here and here and here, whatever data you have, but inside it can go crazy. So you don't hear about this interpolation formula very much. But boy, does it make sense for what we're doing. Now I'm just going to rush through this. Basic idea is that it becomes exact in certain situations. It happens the polynomial degree n minus 1 or less makes it exact everywhere. I just write the linear guy, the quadratic guy, and if that's all I'm interested in, I'm just making a parabola, okay? But 1 point determines a level, 2 points makes a sloping line, 3 points makes a parabola uniquely, and that's what you'll get if this the amount of things I have here is what it says, okay? So that is basically the idea here is that this is showing us that this formula, this expression here, particularly this one, but also this one, is truer than true. This is true for any eigenvalues. It doesn't care what the matrix is that made this thing. Truer than true. Now, orthonormality, you got to have what the matrix eigenvalues tell you. But for this, when you stick in random numbers, it still works. Okay? That is the best I can do right now for getting a proof of the completeness. The proof, and it shows what's going on. All distinct values satisfy that sum, as I say. Truer than true. You can see with just 2 by 2. You just work out 2 by 2 and see what you get. Yeah, it works. Well, that was what I was doing before. But, you know, who's going to believe somebody that says that this thing will work for n? All of the stuff that we've just shown here works for n dimensions. Nobody that's not a critic. I mean, you have to be pretty uncritical to accept that. But boy, it is really neat to see this and then make sense out of this. Okay, well, it's time to get with the physics. I'm going to skip over this particular thing very quickly, simply because we want to get to some physics here. But the basic idea is that you load these kets into the rows of one transformation matrix or into the columns of the other. And there's an example down there at the bottom. Let's put this one full speed ahead, as well as this one. So here's just an example where I had a projection operator that we've been working with, okay? And if you want to get the transformation matrix now that takes you from the xy basis to the Eigen basis, the epsilon 1 and epsilon 2 basis, that's what you need right there. So basically you are sitting here, load distinct bras into the D-tran rows. D-tran stands for diagonalizing transformation, and these guys into the columns. And you've got to write a program to do this if you're going to use all this stuff on a computer. This is the prescription right there. And then you're all set up. This matrix right here, then the thing you're diagonalizing, and then this matrix right here is going to give you a diagonal matrix. That is the representations in the epsilon basis from the representation in the xy basis. So this is just a little piece of plumbing that you have to know if you're going to make use of this stuff in future programming technology. Okay. typical example there. Okay. In standard quantum mechanics, it's really easy to get these things. You make the transformation matrix and then you just do Hermitian conjugate. Okay, so let's get busy here with a matrix that will make some motion for us. And first thing we do with this thing is write the secular equation. Okay, so I need to have a trace of the k with a minus sign on it. The trace of the k is 20. I need a minus 20 for the first, well, I should say the second term in the secular equation. The way we write it, so k squared is the first one. And then I still need the determinant of this matrix. That's 100. And then what I've got to do is subtract the product of -1 and -1. So I get 100, I get 99. This is sort of an awkward looking equation, but it has some very nice solutions. Namely, 9 and 11 are the frequencies squared of this oscillator, double oscillator. So that's not too hard, right? Nice example, okay? Except 9 and 11 get kind of ugly. Well, it makes some pretty nice diagrams, as you'll see. But the eigenprojectors, that's what you want to get right away so that you can see what the eigenvectors look like. And this time, they kind of always look the same when you have symmetry. This is where symmetry is giving an answer that you didn't have to do this. I know right away that I'm either going to get 1 and 1 or 1 and -1 as eigenvectors. So if that didn't happen here, it would be an arithmetic mistake at some point. Okay? So let's keep these things sort of in sync here, because eventually I'm going to be running a demonstration of this particular oscillator for these particular eigenvectors. And in particular, I'll be interested in combinations of them. That's the real fun part of all of this. And that's what happens right here when we talk about mixing the modes. Mixed mode dynamics. We're going to get stuff like that. Okay? Now, what you're going to be seeing here, and I guess we might as well start the thing. Why hold off? I'll do it with the middle screen here. This is going to be the thing that makes those beats. We might as well see how that happens. And then we'll come back and look at this algebra critically, because there's some things that you should know about it. But that's basically what you're seeing, is that thing starts off entirely at this point and then traces all of that stuff. Okay? This is you a pattern of some kind. Now I can run this thing for a very long time so that it just makes a black square, because that right now looks kind of symmetric, but see, getting thicker each time. Okay, so this thing, and we'll talk about continued fractions, telling you that. But the main thing that I want to emphasize about this particular case here, where I'm adding something that has this frequency omega 1, okay, the frequency omega 1 here, that's this epsilon right here, and now I squared that this K1 eigenvalue should be frequency squared. This is classical oscillators, not quantum. We'll be doing quantum shortly, next lecture. But for now, it's always a square of the frequency that you'd be writing into there. And that is being 9 and 11. Okay? So I've got an e to the minus I9 and I've got an e to the minus I11 each times time. And I'm adding these things up. But it's not terribly hard to add these two, which have the same coefficient except for a minus sign, and then these two, which have the same sign even, to get here the sum of the two exponentials, the two Fourier components. That's what you can think of these modes as Fourier components of the space of vectors. This one has a plus sign and this one with a minus sign, okay? And then I factor it with this clever little identity here. And this is a good trick to keep in mind. If you just want to add two exponentials, two phasors, e to the IA and e to the IB, we can factor that thing by just doing a plus b over 2 as your factor times a minus b over 2. That cancels the b, so that gives you e to the IA. And then you go down and put a minus sign on this, that will give you e to the IB. So this is what you're going to see. You're going to see this sum become a product of an overall phase and then something that's real, something that has a shape to it, that has a cosine shape. The group shape here is cosine. Okay, the thing that determines the envelope of all of the oscillation that's contained in this thing. So that's a neat way to think about this plot, but it's also a neat way to think about it if this was a quantum mechanical problem. You can already see that it's the same kind of problem, except for the fact that the frequency is squared. It's quantum mechanics simpler. It's got a frequency of first power. You can see already our things getting thicker and thicker, eventually covering the whole thing. But the basic idea here that I'm going to emphasize is that the beat frequency, that's the thing that you actually see in quantum mechanics. You don't get to see this unless you have a phase-sensitive detector, and a phase-sensitive detector takes the measurement, spoils the whole thing usually. But a classical one, I can go in and look at the stuff that's inside there, as well as I can look at the envelope of the stuff that's inside there. But the oscillation of, if it was quantum mechanics, the probability wave, okay, which is the only thing you get to see, is a difference of the eigenvalues. But strictly speaking, it is the half difference. The half difference is what you're really working with. And that half has to do with spin a half, and we're going to talk all about that in the next lecture as we try to marry classical mechanics to quantum mechanics and using this kind of stuff. But you see right here, omega 2 minus omega 1 over 2. It's a cosine of that. And here's a sine of that. So you have sine, cosine here, and then a sine there. Okay? And you have a sine with an I on it. That's the other thing that you actually see more easily by looking at the phasors that are drawing this thing. So you see what you have here are two mode phasors. One of the phasors here controlling the beginner slope, the slow axis, and then another one right here controlling the fast axis. And I can very quickly demonstrate that thing by simply erasing all the paths and setting my initial condition right here. Remember our graphical way of looking at this thing? Okay, let's get rid of, erase the paths. Okay, so as you can see, that all we're getting here is the fast mode where the thing goes against each other, where the two go against each other, and the spring between them is the thing that's really effective for giving a high frequency. Meanwhile, on the other axis, the orthogonal, the normal to this axis is this one. And let's erase the paths. Now they're together, you see. Now it's not really terribly noticeably slower. One of them is 3.0 and the other is 3.3. You don't see that difference unless you look carefully that this one is got a longer wavelength than the one we had before. We don't have very much of a coupling spring here. It's only 0.15 or 1/6. Okay, but that's what's giving you the beginner slope, the mode that is the slow mode. All right? Is this making some sense? There's a lot of physics and math being piled on top of each other, but the idea is that if you get them sorted out, it's really beautiful. Something you won't forget. But it takes some time. Okay? Okay, now, the rest that I would like to talk about before we go too far on this, and I could just show you these. Look, that's this thing right here, but This is a demo that really is hurt by friction. It doesn't last very long, but you can see the beating going on there with this. And I can go ahead and start this thing right here and just do one real quickly. What I'm going to do is pull this thing without disturbing the other one too much. We'll pull it out so that it's out at unit 2. And you see the energy going pretty much in that one and not in that one. Let me do a better job of starting this thing off. I think I will just give it a shove. So that thing that I shoved very quickly lost, and now I gained it back again. So that's what you're seeing when I have both of the modes running at the same time. And on a simulation with no friction, it's so easy just to go here and let her get bigger and bigger ellipses until it's on a horizontal, and then it returns fairly quickly to the vertical. Okay? And you can see these two guys, now it's a longitudinal mode, but these are transverse, but other than that, it's the same thing without friction, so that it goes forever. Okay, let me go ahead on this one. This is just a picture of what we were doing with a very much nicer selection of coupling parameter, the bilaterally symmetric coupling parameter for that one. And then a picture of the control panel that you get when you click on this thing. And I recommend you do that. But I also want to show you this. And that is when I perform this particular one, and I'm going to do that right now. I'm going to go ahead and pause this guy and go over here. Back to the lecture. Go ahead and pick up on this one. And I'm particularly interested in that setting, so I'll leave it here and let it run so that you can actually see what it is that it does, and let's hope it works. And it's a little slower than the other, that's nice. So here comes, we've just finished one beat. We went from being horizontal to vertical. And by the way, this is also a study in optical polarization. This is a quarter wave plate. If I were to stop it after I'd taken a horizontal polarization and turned it into vertical. So all of the stuff that happens in optical polarization is being described very well by all of these. But the thing that I wanted to point out was, and let's just stop this one so it isn't being something an applause there. What I want to do is just calculate how many times does this thing go through the x-axis and how many times the y-axis, or let's do the diagonal instead. This is the eigenbasis. I go 1, 2, 3, 4, don't count that, 5, 6, 7, 8. Now let's see if that, oh no, I missed one right there. There was one that went right through. 9. What I do is, let's do it again. 1, 2, 3, 4, 5, 6, 7.
I counted it this morning.
What I'm used to. I'm hoping I can get 11 over 9. What did I miss? 1, 2, 3, 4. And then this is a fifth right there. 6, 7, 8, 9. I haven't learned to count yet. You have to excuse me on that count, right? Okay, and then go on the other axis and see how it cuts across there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is a 9 to 11 Lissajous pattern. Okay. Now this is just more of that stuff that we did with the eyeball and you did on the homework with the cone, right? There are certain settings that give you a perfect periodicity. And that's what we're getting here. The thing hasn't expanded and covered the whole space. It's not ergodic, it's the opposite of that. And this is where the ratio of frequencies is important, not the difference. The difference is what you usually measure just to get your transition frequency. If you have a two-level system, that's the only frequency you can see. You can't see the frequency of the phase here and here. You can only see the difference. That's the way quantum mechanics works. Classical, you get to see everything that's moving. Okay? And in a coherent state of a quantum system, you get to see everything that's moving, right? If you make enough quanta, so it doesn't count if you destroy some of it. But what I wanted you to see, and this is in the textbook, I'm just putting it down here, is the way you figure out what those licitudes are going to be is you use continued fractions to expand whatever ratio you might have come up with. If for some reason I made this thing run at pi, I study its convergence by writing down the number, okay, that I'm interested in, okay, and then I call that A0, and then I take an integer of that number, okay, and I calculate A1, which is A0 minus this truncated version, all of the decimal places except 1, and write that down. And then I do it again. I take the integer of what I get from that A1, that's 7, okay? I put that 7 in here with the A1 in the denominator. I get 1599. I do this again and again. Each time I get one of these numbers, I get to make a continued fraction. Here's 3 plus 1/7. After I got to this stage, here is 1/7 plus now 1/15. Okay, and that's what I got from this. And then I go still some more, a continued fraction. I keep getting these integers on the outside here. And the next step gives you this. And look at how very quickly I get a pi to pretty high precision. Okay? Not so much for the golden mean. So this is a number that is, well, it depends on, I would call this a fairly rational, irrational number. This is the most irrational number. Look at it, it's so terrible. I mean, it doesn't look any different at first glance, but you'll see here, you know, I'm already down here where I'm getting 3141592. Well, that's wrong, but I've got all those decimals are right. I only got 1 right here. Only 1. And I get down to here, I got 2. And down to here, I get 3. It's horrible. So this is a really irrational number. So I challenge you to set the golden ratio on one of these things and see what it does. That's a real lesson in coherence, or chaos versus order. Chaos versus, this is a very ordered thing here, nice little thing with a ratio 11:9. Okay, so I point that out right here. I said polarization in two-level systems. This stuff, we'll come back to this geometry later on. This is a geometrical way to describe how the eigenvectors are evolving from being all in one place, that's what we did here, started out with everything in the x-axis, and then it goes a little bit to the y-axis, it goes completely to the y-axis. That's a half-wave plate if you're thinking of optical polarization. In between we get elliptical polarization and circular polarization at halfway point. So think about this as a way to understand two-state systems that we'll do later on. Now here's a really nasty oscillator with all kinds of horrible numbers being used. Here masses are still equal, but everything else is lopsided. And what this one gives you, I'm just going to skip ahead since we are at the end of the period here. We go ahead and make the Ket-Bras and see what the eigenvectors look like, and see what you get for this one. This one is really quite beautiful. And I'm going to go ahead and I'm going to get this one down here up to that point, if I can. YouTube is taking over, but I think now I can get rid of that. So just so you have a record of what it is we're going to be looking at, and then we'll talk about what it makes. And I'll stop right there for this one. This one plots a parabola. You know, we've been making all these funny things with sines and cosines, but this one plots a parabola. And let's just see if I can make it do it, actually do it here. Yep. Da-da, 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 da-da. It's a parabola. Or it looks like a parabola, and that I'll leave you to actually prove it is a parabola. But this is quite remarkable. And if I go ahead on this one down here, we see the fellow that really was responsible for making not just parabolas, but any sort of closed polynomial out of sines and cosines. Mr. Chebyshev. You see the pronunciation is written next to that if you can read it. I'm going to pause this guy right here. This is sort of intermediate complexity. This is the simplest possible thing you could think of at first for a mode structure.
Non-trivial.
I'm going to go back here and go ahead on this one so you can read it fairly easily. This one has the eigenvalues up at the top there. 4 and 16, you think that should do something amazing. Indeed it does. Makes a parabola. Okay. This is actually working out what happens right there. Sure enough, it is a parabola. There's the normal coordinate square times 4/3 plus half. That's what it is. Now, anytime I click on this one, I'm going to get another parabola. If I just click without adding any velocity, okay, and of course if I do it right on the mode, I get a straight line. That's a subset of all the parabolas that I can make here. Okay, but if I am so inclined, I can add a little velocity to this. Let's erase the paths that were there before. Now I get a parabola that's been rotated in a funny kind of way. Okay? So right down the middle of that thing is a parabola. If I can put my thing there and don't give it any velocity, I split the residue cleanly into a parabola. Well, this is the kind of stuff that Mr. and what is his name? Alternative Chebyshev, I mean, they just keep going here with these pronunciations.
Oh, yeah.
It's a Russian name, okay? You can pronounce it any way you want as long as he's not listening. If he is listening, he's going to hit you. Okay? So, these are, what we've just made here is a second order Chebyshev polynomial. Ooh, cool for other things. Okay. Well, I hope you've enjoyed the beginning of this. We're going to be going deeply into the spinor treatment of all of this motion. And that's very valuable, again, for polarization. Right now, polarization optics is becoming so sophisticated that almost every field that has anything to do with light looks at it and gains from it. So understanding it is just as important as understanding other two-state systems. The spin half, of course, is the first one that most people are taught in quantum mechanics. But photon has spin 1, but only 2 of the dimensions of spin 1 get used, so it becomes a U2, a problem. And that's what we'll be looking at more of. Okay, we'll see you. The homeworks, as I said last time, are now in the mailboxes. So